When you operate the brakes on a moving car, the braking efficiency and stopping distance are both governed by the tyre's grip on the road surface. Assuming the braking system is in perfect working order, improved retardation can only be achieved by advances in tyre technology or better quality road surfaces. And even when these optimum conditions do apply, absolute braking efficiency cannot be guaranteed, especially when the driver encounters treacherous conditions such as wet, loose or icy road surfaces. To cope with these conditions, the driver has to soft pedal on the brakes to prevent one or more wheels from locking up, causing a loss of steering control if either or both front wheels lock. And if the rear wheels lock, the car is likely to spin completely out of control. Alternatively, if a driver needs to brake suddenly on a bend, this can also lead to a dramatic loss of control, resulting in a skid. Finally, in a panic braking maneuver, perhaps caused by some unexpected obstacle, a driver may have to slam on the brakes to stop the vehicle rapidly, with equally disastrous results. The effective solution to all these driving hazards, even for the most skillful driver, is to have a braking system that takes maximum advantage of available tyre grip without causing the road wheels to lock, except at a specified low minimum speed. And that's why Fiat have developed an ABS anti-lock braking system for the Chroma. The secret of ABS is an electronic device that prevents the road wheels from locking whenever the braking effort threatens to overcome the grip of the tyres. The anti-lock braking system also maintains the car's stability irrespective of road surface conditions and ensures that every ounce of tyre grip is fully exploited. Even under panic braking conditions, ABS helps the driver maintain directional control of the car without the risk of skidding. In this way, the system helps any driver obtain the kind of braking precision that previously only expert professional drivers could expect to achieve. To be effective, the system needs to be both precise in the way it responds and rapid in reaction. Both these criteria are achieved as a result of using electronic controls that combine reliability, accuracy, and fast response, together with a minimum number of components and minimal cost. To understand the system's operating functions, perhaps we should briefly examine a few basic concepts. Immediately a car's brakes are applied, the tread pattern of a formerly free-running tyre alters. This tread condition is known as braking deformation, which is caused by the difference in its rotational speed in relation to the car's linear speed. Maximum deformation occurs when the road wheels are completely locked on a moving vehicle. The resultant slide or skid factor, which varies according to the speed of the moving vehicle and the reduced speed of the rotating tyre tread, can be expressed as a percentage. For example, when a road wheel is turning freely with no braking effort being applied, the skid factor is 0%. Conversely, when a wheel is completely locked by the brakes and the car's moving momentum continues, the skid factor is 100%. Research has shown that the most effective braking conditions are obtained when the skid factor is between 5 and 20%. The need to keep skid factors within very precise limits is imposed by tyre behavior during braking, when the coefficient of braking friction takes effect. The higher you can make this coefficient, the more effective your braking will prove. From this simplified chart, you can see that the highest coefficient of braking friction corresponds with skid factors between 5 and 20%. Since the coefficient of friction is directly proportional to the braking force applied, the anti-lock braking system is designed to apply maximum braking force related to the optimum coefficient of friction. For Chroma, ABS has been incorporated in the existing braking system and comprises the following parts. Firstly, 4 sensors, monitoring the rotational speed of each individual wheel. Secondly, an electronic control unit that receives the signals from all 4 sensors. Being effectively a mini-computer, it is protectively located in the driving compartment. Thirdly, an electro-hydraulic unit, located in the engine compartment, which regulates the braking force applied to the brake calipers by means of 4 solenoids, that is, 1 per wheel. The rest of the system comprises the following elements: securely located hydraulic pipework, an electrical wiring system, and 3 relays, the function of which will be explained later. A warning light on the fascia, which operates intermittently if there is a system malfunction. A switch on the brake pedal to activate the electronic control unit when the brakes are being applied. The reason why Chroma's ABS braking system has 1 sensor for each road wheel is that research has shown that this proved the best system for front-wheel drive cars with a diagonally split hydraulic brake circuit. Major benefits of this configuration are improved maneuverability and stability during braking, together with maximum retardation. All 4 sensors are of the inductive type, applied to fixed suspension components. Here we see one of the front wheel sensors, and here a rear wheel sensor. The front sensors are mounted on the suspension by securing clamps, with shims inserted to adjust the air gap. The corresponding phonic wheels with 92 teeth are keyed on to the constant velocity joint of the transmission, supplied as 1 integrated unit. The rear sensors are mounted on the suspension stub axles, again using clamps with adjusting shims. The rear phonic wheels, also featuring 92 teeth, are keyed onto the wheel hub and supplied as 1 integral unit. The electronic control unit is a highly developed component resulting from painstaking research. It is connected to the system's wiring loom by a multi-plug with 35 connections, 23 of which are utilized. This unit takes advantage of large-scale circuit integration and consists of a printed circuit with resistors, diodes, transistors, and integrated logic circuits. The electro-hydraulic unit is connected to the brake servo and brake calipers by the braking system pipes. The same unit also houses the 4 solenoids that regulate the pressure for each brake caliper in response to the signals supplied by the electronic control unit. Let's now look in detail at how the ABS system works. To start with, the following aspects of the car's performance must be continuously monitored: running speed, acceleration, deceleration, skid or slide factor. The 4 individual wheel sensors supply information to the electronic control unit that in turn affects the operation of the electro-hydraulic unit. The sensor signals are generated by lines of magnetic flux passing over the teeth of a metal ring rotating with the road wheel. The alternating pattern of teeth and intermittent gaps creates an induced electromotive force at the sensor terminals, causing an alternating signal to be transmitted to the electronic control unit. To operate correctly, the distance between the sensor and the toothed ring, known as the air gap, must be set to a predetermined tolerance. The toothed ring is called a phonic wheel because the signal it generates has the frequency of a sound wave. The frequency of this signal defines the speed at which the wheel is turning. Any increase or decrease in the frequency corresponds with the vehicle's rate of acceleration or deceleration. The signals from the sensors pass to the electronic control unit and enable it to determine the rotational speed plus deceleration or acceleration rates for each wheel. The electronic control unit monitors the signals from the sensors to evaluate the rolling conditions of each wheel when the brakes are applied. It processes these signals and compares them with reference values stored in its memory. Based on this information, it commands the individual solenoids in the electro-hydraulic unit to either reduce, increase, or maintain the pressure on the calipers in order to maximize braking efficiency. The ABS system continuously and rapidly monitors slide, deceleration, and acceleration factors for each wheel to ensure controlled deceleration during braking. Since the operating conditions the control unit monitors are directly affected by the inertia of the wheel and tire assembly, it's important that cars equipped with ABS are always fitted with wheels and tires recommended by Fiat. However, if a vehicle is fitted with snow chains for driving on hard-packed snow, the anti-lock braking system still functions efficiently. The electronic control unit also has a safety circuit to check that the system is working each time the car is started and continues to work properly while the vehicle is on the move. If the safety circuit detects a malfunction, it prevents the ABS system from being used whilst retaining the normal operation of the conventional braking system. In this situation, a warning light on the fascia glows to advise the driver that ABS is not operating. The same circuit also monitors battery voltage and switches off ABS if the voltage is too high or too low. Another integral part of the safety circuit is an active section called the test cycle, or BITE, standing for built-in test equipment. This section is activated by voltage from the wheel sensors. It uses a program and test signal to verify that the electronic control unit, including the safety circuit itself, is working properly. As we've already seen, the electronic control unit sends commands to the electro-hydraulic unit. Here we show a simplified diagram of the inside of this unit with the circuit for controlling a single wheel. It contains the following elements: a solenoid activated by the electronic control unit. In fact, there are 4 solenoids, one for each wheel. An electric scavenge pump with inlet and outlet valves of the opposed piston type, ensuring that the duplex system works properly. An accumulator. The unit has an accumulator and damper for each duplex circuit. In relation to the signals received from the electronic control unit, the electro-hydraulic unit adjusts the pressure exerted on the calipers. There are 3 phases. 1, an increase in pressure phase. 2, a reduction in pressure phase. And 3, a maintaining existing pressure phase. In the increasing pressure phase, the solenoids are not activated. The pressure of the brake calipers, shown in red, is that exerted by the driver's foot on the brake pedal. The braking force applied and the degree of road grip exerted by the tire could result in such a dramatic retardation as to risk causing a slide or skid. In this situation, the control unit detects that the wheel is decelerating too fast, which causes the ABS system to operate and adjust deceleration to preset levels. In turn, this causes the reducing pressure phase to take over. The solenoid is activated by a current of about 5 amps, and the resulting movement of the piston, shown in white, blocks off the connection between the brake servo and brake caliper. Simultaneously, the connection between the brake caliper and the scavenge pump, influenced by the electronic control unit, is opened. Consequently, brake fluid flows away from the brake calipers and the pressure they exert is reduced. The scavenge pump circuit passes the brake fluid withdrawn from the calipers back into the main brake system. At this point, the solenoid is energized by a current of about 2 amps and the maintaining existing pressure phase takes over. The connections between the brake servo and brake caliper, as well as those between brake caliper and scavenge pump, are blocked off, so the system adopts a waiting mode. The pressure at the brake caliper is maintained at the level previously reached, regardless of the pressure applied by the driver's foot on the brake pedal. With this degree of braking force, the rotational speed of the wheel increases and approaches the linear speed of the car. When the permissible threshold values are reached, the braking force is again increased. This alternating cycle is repeated as long as necessary to bring the car to a halt. The effects of this cycle can be detected by the driver in the form of intermittent pulses on the brake pedal during braking operations. This is perfectly normal when ABS is operating. In this way, ABS braking operates progressively by degrees, with alternating phases of pressure succeeding each other, dictated by the prevailing road surface and tire grip conditions. The cycle of phases is repeated rapidly until the braking operation is efficiently completed. Despite the fluctuating pattern of braking force, there is no impression of jerkiness, mainly due to the high speed at which cycles are repeated and the smoothing effect of the road wheel's inertia. Normally, a driver could pump the brakes twice every second, comprising 2 depressing and 2 releasing actions. With ABS, though, for a single operation of the foot pedal, the number of cycles increases to 4, 10, and up to 18 a second. This results in a smooth, controlled braking action, with the car's speed reduced in a smoothly controlled way, without a trace of jerkiness. Normally, ABS ceases to operate at maneuvering speeds below 3 miles per hour in order to allow the wheels to lock fully, bringing the car to an immediate standstill. To control the 2 solenoids in the rear circuit, the electronic logic uses the so-called select low approach. This applies, for example, when the car is being driven along a road with intermittent wet patches and the tire grip differs between front and rear wheels. Our illustration shows dry road shaded in a light color and wet road represented by the dark area. As soon as the brakes are applied, the wheels decelerate. Because of the difference in grip, the tires on the wet surface slow down more rapidly than the ones on the dry road. Signals from the sensors detect this difference in the speed of wheel rotation and make the electronic control unit react accordingly. Its response is to command the electro-hydraulic unit to supply both rear wheels with the same braking force as the front wheels, which have less grip. The electro-hydraulic unit is connected to the braking system by outlets with the following identification marks. VR to the front offside caliper. HL to the rear near side caliper. VL to the front near side caliper. HR to the rear offside caliper. The same identification corresponds with the 4 solenoids. On the left, you see the inlet from the servo for the circuit for the front near side and rear offside wheel. On the right, you see the other inlet from the servo. Beneath the cover, there are 2 relays, a solenoid relay and a scavenge pump relay. On the base, there are a series of electrical contacts connecting the unit to the battery, the main relay, the electronic control unit, and one of the system's earths. The red cable is the supply cable for the pump relay from the battery. This is the screw for fastening the earth braid. The electro-hydraulic unit cannot be overhauled and must be replaced if it develops a fault. The only 2 components which can be replaced are the 2 relays. As previously stated, there is a warning light on the fascia alerting the driver to the fact that the ABS system is switched off because it's developed a fault. We'll now see how this warning is given. With the ignition switch in the on position, the warning light on the fascia comes on. As soon as the engine starts up, the warning light goes out. The signal that the engine is running reaches the electronic control unit from the alternator, to which it is connected electrically. At about 2 miles per hour, the anti-lock braking system becomes operative. At about 4 miles per hour, the cycle for testing the system, excluding the wheel sensors, begins. If the responses from the components in the system are satisfactory, the warning light stays off. Conversely, if an unsatisfactory response is received, the warning light comes on and the ABS system is automatically switched off. If this happens, the car's retardation is dependent on the conventional braking system. In this phase, the warning light may operate intermittently. At about 15 miles per hour, the bite circuit tests the wheel sensors. If the warning light comes on at this speed, followed by the ABS system being switched off, the fault probably lies in one or more of the sensors. Obviously, these values are simply for guidance and should not be relied on for correct diagnostic interpretation. If the battery is not being charged adequately, the warning light may come on and the ABS system switched off for as long as the low voltage condition persists. For example, this may happen when driving in slow town center traffic with all the electrical systems switched on. Now let's examine the electrical system. As previously stated, the ABS system has its own specific electrical wiring. The electronic control unit is connected by a multi-plug, and so is the electro-hydraulic unit. There is one relay in the electrical system which we have not yet referred to, namely the main relay. Its function is to supply both the electronic control unit and the electro-hydraulic unit relays. It contains a protective fuse for the whole ABS system and a stabilizing Zener diode for protection against overloads. If the fuse is faulty, the whole relay has to be replaced. The relay is activated when the ignition switch is in the on position. In this state, the relay supplies the electronic control unit and the activating circuits for the following two electro-hydraulic unit relays. The solenoid relay, which if activated by the main relay, enables the solenoids to be supplied with current as and when commanded by the electronic control unit. The electric scavenge pump relay, which if activated by the main relay, enables the electric scavenge pump to be supplied with current, again when commanded by the electronic control unit. In the electro-hydraulic unit socket, between connections 10 and 12, there is a diode which acts as a supplementary control for the ABS system warning light. If the electronic control unit's multiplug should become detached or is incorrectly connected, the warning light comes on. The switch on the brake pedal signals the electronic control unit that the brake pedal is being depressed whenever the car is running with the engine on. By means of the connection to the alternator diode bridge, the electronic control unit is advised that the engine is running, and it intervenes by turning off the ABS warning light. When carrying out repairs or servicing operations on the ABS system, a number of precautions must be observed. If any welding operations are carried out on the car, the plug must be removed from the electronic control unit. During repainting, the electronic control unit can be briefly exposed to a maximum temperature of 95 degrees centigrade or to not more than 85 degrees centigrade for a longer period of time, such as 2 hours. If any of its components are replaced, for example following an accident, the entire anti-lock braking system must be checked with the test equipment. When securing the electro-hydraulic unit to the body shell by means of its 3 anchoring points, only 2 of which can be seen here, care should be taken to ensure that it's perpendicular, or with no more than a 5-degree tilt, either longitudinally or transversely. The electro-hydraulic unit is pre-filled with brake fluid and supplied with its solenoids in the open position. Bleeding and refilling the braking system is carried out in exactly the same way as a conventional braking system except that it takes longer due to the extra volume of fluid and some extra narrow sections. Whatever work is done on the hydraulic section, it must always be followed by tests with the appropriate diagnostic equipment to ensure it is working properly. After any of the connecting pipes have been loosened or removed a few times, they must be checked for signs of leaks. No other pipe union should be loosened, tightened, or even worse, removed. Another important aspect of pipes involves checking to ensure that they have no direct contact with the body shell. This is vital to prevent damage to the protective coating of the pipes themselves and to avoid the transmission of noise when the ABS system is in operation. The servicing procedure requires a check to be made on the air gap between the sensors and the teeth mounted on the wheels. Special care should be taken to ensure that these components are positioned correctly, as the system can only operate efficiently if the signals transmitted are correct. If the gap between the sensor and phonic wheel is too wide, the signals transmitted will not be sufficiently clear. Conversely, if the distance between them is too narrow, the phonic wheel may interfere with the sensor, causing damage to both components. The setting for this air gap, for both front and rear sensors, should be 0.7 plus or minus 0.15 millimeters. If this is not the case, the air gap for the front sensors can be adjusted by using the 0.3 millimeter thick shims under the sensor fastening bracket. To determine how many shims are needed to adjust the air gap to the correct setting, proceed as follows. Measure the existing air gap, which in our case is 1 millimeter. Since each shim is 0.3 millimeters thick, it is obvious that by removing one of them, we should achieve the correct air gap of 0.7 millimeters. In other cases, simply add or subtract the number of shims that results in an air gap close to 0.7 millimeters. Lastly, check that the correct air gap has been obtained. As you can see, this operation does not prove difficult. To check the air gap on the rear sensors, proceed as follows. Remove both the sensor and existing shims. Insert a 0.7 millimeter thick gauge through the slot in the protective disc as far as the phonic wheel. Refit the sensor without adjusting the shims. Tighten the securing screw and note the distance between the sensor and its bearing surface, which in our case is 1.5 millimeter. Divide this distance by 0.3 to find the number of shims to be fitted in order to close the air gap to 0.7 millimeters. Adjustment of the load proportioning valve must be carried out in the manner specified for a Chroma not fitted with ABS. There is a special item of equipment for carrying out diagnostic checks on the system, namely the Fiat model PR01 electronic analyzer, which comprises a control unit incorporating the fault-finding tester, a connecting lead fitted with a connector equipped with some of the most commonly used pins, a connecting lead fitted with a cigarette lighter plug, a set of sample resistors soldered on standard plugs, and finally, a manual featuring troubleshooting cards. The Fiat electronic analyzer has been developed to make diagnosis of the ABS system easier, even for servicing personnel without previous training on the electronic equipment currently fitted to cars. Instructions for using the electronic analyzer are supplied with the instrument. The device is connected to the system as follows. Remove the system's connector from the electronic control unit. Connect the electronic analyzer to this connector. Then, carry out the sequence of tests specified in the instructions. It's essential to follow the sequence of operations specified and rectify any faults before moving on to the next test. After every servicing operation and subsequent check with the diagnostic equipment, the car should be road tested in the following manner. Turn the ignition switch to the on position. The warning light should come on. Switch the engine on. The warning light should then go out. Test the brakes a few times, and if the warning light remains off, everything is okay. As for every other Fiat model, a special manual for the Chroma is supplied to the network by the Technical Assistance Service. This contains further information about the components of the ABS system featured in this video training program. It also shows in greater detail how it works, how to diagnose faults in it, and how to set about rectifying them.